Well, let's take a moment to consider how to calculate power for an AC circuit. So again, you see the diagram of the inductor, resistor, and capacitor all connected in series with the generator. For a moment, I want you to consider the case where there's practically zero inductance or capacitance, and you're just powering a pure resistor with a generator. In that case, the phasor diagram would only have two phasors. The current phasor, capital I, and then the voltage across the resistor, which is always in phase with the current. So if we want to calculate power, at any given instant, power at any instant is equal to instantaneous current multiplied by instantaneous voltage. So let's look at the instantaneous values of current and voltage across the resistor. Those are just the projections onto the x-axis from the phasor diagram. So the current is current amplitude multiplied by cosine omega t. Here we have an angle, right? This is the x-axis you can think of as t equals 0, and so the phasors here are shown at some moment in time t prime equal to, 0 plus some small amount of time dt. So here's omega t prime. Now we can just call this, look, why mess with this? Just call this some other time t. So this angle here is just omega t. There we go. So I have to multiply current times voltage. The voltage is V, also cosine omega t. Right? These are just the instantaneous values of current and voltage are just the adjacent sides in a right triangle with an angle of omega t. So we find that the instantaneous power is equal to current amplitude times maximum voltage times cosine squared of omega t. So if we were to graph the power, it varies in time. And we don't notice this with our electrical components. If you turn on a light bulb that's powered by AC, like all the light bulbs in your house, it doesn't seem to be flickering on and off because the frequency is so high, it's at 60 hertz. Although you can hear, in some electrical components, you can hear, especially lights like fluorescent lights that are powered off of a ballast, you can hear the humming of the ballast with that 60 hertz frequency. So a graph of cosine looks like this, but a graph of cosine squared, that's what we have here. A graph of cosine squared has the same shape as our graph of power versus time, and so that looks more like this. So there are moments in time where the power is 0, but there's an average value of power. Now we've already gone over this before when you probably saw the lesson on rectified average values and root mean squared values. And in that video, you saw that the average of cosine squared of anything, cosine squared of omega t, or cosine squared of theta, or cosine squared of x, the average value of cosine squared is just equal to 1/2. So instead of instantaneous power, we can express average power as 1/2 the current amplitude times the maximum voltage. Oh, and remember that the RMS value for current is 1 over rad 2 times the current amplitude, or in other words, current amplitude is rad 2 times the RMS current. And in the same vein, maximum voltage is rad 2 times RMS voltage. So if we make those substitutions, we can say average power is equal to 1/2 times rad2 RMS current times rad2 RMS voltage. But rad2 times rad2 gives us 2, and 2 cancels 1/2. So isn't that simple? Average power is just RMS current multiplied by RMS voltage. Easy. But again, that's only if our circuit just has resistance and we ignore inductance and capacitance. Let's imagine a case where we connect a generator strictly to an inductor. Well, the graph of current versus time, if we say I equals current amplitude times cosine omega t, then we look at our phasor diagram, we see the current phasor points here at some time t, so there's omega t. Then the voltage across the inductor leads the current by 90 degrees, Eli the Iceman. So the graph of current is a graph of cosine. Oh, I guess this is lowercase I, max value is expressed as capital I. But the graph of voltage then is 90 degrees out of phase. It's 90 degrees ahead, so that gives us a graph of negative sign. So if we plot these together, we have something like this. That looks about right. Well, let's see. The values of current are all positive all the way up to here, but the values of, let's see, this is plotted both things on one graph, haven't I? So this is current and voltage across the inductor graph together. So label this clearly. This graph is the current, and this graph is the voltage across the inductor. So the current is 0 when the voltage across the inductor has its maximum value. And likewise, the voltage across the inductor is 0 when the current has its maximum value. And there are some moments in time that both the current and the voltage are both positive. For example, from this point in time up until this point in time. And a positive times a positive obviously yields a positive. And there are moments in time when both these values are negative. For example, from this moment in time up until this moment in time, and a negative times a negative also yields a positive. But for all of those, if we cancel out those intervals, we can see in all the other intervals, one of the values is negative, right? There's negative, and the other value is positive, and a negative and a positive give a negative. You know where I'm going with this. What do you think the average is when you multiply current times voltage, but the voltage is 90 degrees off from the current? Yeah. The end result is that the power is equal to 0. The average power. Now at any given instant, no, in some instance it's positive, in some instance it's negative, and so on, but the average value is 0. Now the exact same can be said for the capacitor. The graph of current is cosine, and then our graph for voltage would be a graph of positive sine. But anyway, we can make the same argument that for half of the cycle, you either have positive current and positive voltage, or you have negative current and negative voltage. But for the remaining half of the cycles, you would have either positive current matched with negative voltage, or negative current matched with positive voltage. And the average, the end result of all this, is that the power to the capacitor is also 0. So What we really need to determine is what's the power when all three circuit elements exist together in the circuit: the inductor, the resistor, and the capacitor. So on average, we can treat that as there's no power, but by virtue of having inductance and capacitance, now our phasor diagram, we've got voltage across the resistor. Maybe this is something driven at a fairly high frequency, so voltage across the inductor is greater than the maximum voltage across the capacitor. And you've seen this before. That means there's going to be some sort of phase angle. There's a phasor that can be represented to show the difference between the voltage across the inductor and the capacitor. The voltage across the resistor remains. So we use the parallelogram method for adding. We find the overall voltage in the circuit is not in phase with the voltage across the resistor. And by the way, we think of voltage across the resistor as being synonymous with the current. So the current phasor and the voltage phasor are at a phase with one another. If power at any instant is equal to instantaneous current times instantaneous voltage, now we have power at any instant equal to current amplitude times cosine omega t. Let's show that angle omega t. We see what the angle phi is. Phi is the angular difference between the current phasor and the voltage phasor. Omega t is just how far into the cycle has our phasor diagram rotated. If we draw this phasor diagram later in time, then maybe the voltage across the resistor points here. Well, that just means the phase that represents the difference between, let me label it, the difference between the voltage across the inductor and the voltage across the capacitor. It's got to lead the voltage across the resistor by 90 degrees. We apply the parallelogram method, and we end up with the same angle phi, the difference between the overall voltage and the current. I just draw the current phasor parallel to the voltage across the resistor. But now the angle omega t goes all the way from the positive x-axis to our current phasor. So don't confuse phi with omega t. Phi is the phase angle, and it really just represents whether or not the circuit is driven far from resonance or closer to resonance. So, carrying on with the derivation here, starting from point 1, just a basic expression. We know that power is the product of current and voltage. So by substituting, we replace current with I cosine omega t, and then we have to replace voltage with max voltage times cosine, now not of omega t, but of omega t, what the angle is all the way to here, it's omega t plus phi. I guess I should use proper symbols for parentheses. Okay, so now in step 3 we have the instantaneous power is current amplitude times max voltage times cosine omega t multiplied by cosine omega t plus phi. Now let me see if I've got this right. I'm going on memory here. How can I expand this? Is this the same thing as cosine omega t sine of phi minus sine of omega t cosine of phi? I think I have that right. Carrying on, our instantaneous power is equal to current amplitude times max voltage times, now I've got to distribute all this together. Let's see, combining here we get cosine squared omega t sine of phi minus cosine omega t sine omega t cosine of phi. Oh, no, I think I've made a mistake. I see it. This is, I think I have these backwards. I believe this is sine omega t oh, that's it. No. It's cosine omega t cosine phi minus sine omega t sine phi. There we go. I'm going to backpedal. Do-overs. Yeah, let me make the right substitution here. This is cosine omega t cosine phi minus sine omega t sine phi. There we go. So step 4, instantaneous power is equal to current amplitude times voltage times, there we go, cosine squared omega t cosine phi minus cosine omega t sine omega t sine phi. Looking at this part of the expression, this reminds me of what we just said earlier in this video presentation here. I know it got a little messy, but what do we get when we have a product of cosine omega t and negative sine omega t, right? This is a graph of negative sine omega t, and we had a graph of cosine omega t. The result on average is a product of 0. So all of this goes to 0, gone. And what's the average of cosine squared of anything? Right. On average, that's 1/2. So the average power is equal to IV times 1/2 times cosine phi minus 0. So average power for a circuit that has all of the components, it has inductance, resistance, and capacitance. In that case, the power is equal to 1/2 times the current amplitude times the voltage times cosine phi. And then we can make the same argument again. We can say that's the same thing as I RMS, V RMS, cosine phi. So this term cosine phi is called the power factor. Now think about it. If, let's say the frequency is really high, so the driving frequency is much larger than the resonant frequency, then in that case we'd be taking the cosine of nearly 90 degrees, which is 0. And by the way, if the driving frequency was much, much less than the resonant frequency, then we'd be taking cosine of negative 90 degrees, which again is almost 0. So what's the language we use? We say when we drive an AC circuit at really high frequencies, the circuit's going to behave inductively. It just means the phasor diagram might have voltage across a resistor that's some reasonable length, and lagging behind that is voltage across the capacitor. Now leading the voltage across the resistor by 90 degrees would be an extremely large voltage across the inductor. The reason it would be very large is because voltage across an inductor is inductive reactance times current, but then again inductive reactance is frequency times inductance times current. So with really high frequency comes a very large voltage, and what happens is it's guaranteed to shift the, if we use the parallelogram method on this one, we're going to have an overall voltage that's nearly in phase with the voltage across the inductor, and our phase angle is going to tend toward positive 90 degrees. And so the power ends up being fairly low in such a case, because cosine of a very large angle approaching 90 degrees is going to approach 0. And so the same is true if we have a circuit that behaves capacitively. Then I'll let you consider what the phasor diagram would look like, but I think you'll agree that that means the phase angle tends toward negative 90 degrees, and therefore the power factor goes towards 0. So you don't deliver maximum power unless you drive your circuit at the resonant frequency. And of course, if the driving frequency equals the resonant frequency, then our phase angle is 0, and cosine of 0 gives us 1, and then our average power is just I RMS times V RMS. So at any phase angle other than these extremes, if the driving frequency is either just a little bit greater than the resonant frequency, or if the driving frequency is just a little bit less, then we have a phase angle that's certainly not as great as positive 90 degrees and something more than 90. And all we have to do is take the cosine of that phase angle and then multiply it by the product of RMS values for current and voltage, and we'll have found the average power for the circuit. Okay, moving on. Thanks for tuning in.